Welcome, Bill. Bill, well-known speaker, has graced us with his presence. We're very happy to have him to talk about this very topical subject of generics in Go, which is I'm very excited about anyway. Go for it, Bill.
Okay, thanks. Thanks for having me tonight, too. I really do appreciate it. I'm giving this talk primarily to try to give as many people as possible an opportunity to see the syntax, to get a feel for me to teach it, because most of the discussions are happening on the mailing list and in the issues, and there's a lot of us who don't have time for that, and there's a lot of us who are working every day, and we don't have time to look at this stuff. But it is so important that as much of the community gets an opportunity to express their thoughts and opinions and share ideas in order for this, at least first release of generics, to be something that we're all really proud of and we feel comfortable having in the language. So I'm going to be dropping 3 links in the chat window. The first link is to the GitHub repo where the code is that I've been experimenting with, and the code that I'm going to be sharing with you. I won't be sharing all of that. We don't have time. I'm going to lock myself into 1 hour to share the first 6 examples there. I've been capable of doing that, so that's my goal, and then we'll have time after for questions and comments. The second link is a link to the draft document for generics, and the third link is a survey from the Go team, where you get a chance to express your thoughts and opinions as well. Most of those questions are open-ended right now, so it's your opportunity, and it's anonymous, to start to provide feedback to the language team. They are looking at the answers to this survey, so it gives you that opportunity. Okay, so let me share my screen here as we continue to move forward. Okay. And again, the goal for me over the next hour is to try to teach the new generic syntax. So I'm going to try to showcase the bulk of that to give you kind of this kind of more well-rounded view of what's there. And then after the talk in an hour, I'll answer those questions. And please feel free while I'm talking to chat there on the Zoom chat, talk and express your thoughts and ideas, and let's make that part of it interactive, even though I'm not going to be able to interact with that while I'm talking. But I think as a group, it's fun to kind of have those conversations. And even if you see something that you're just like, oh my God, I mean, it's fine, right? Like just talk about that as we're going. Now I'm gonna go through, this is the training repo. I've got a folder called generics. I'm going to try to get through the first 6. That's all I can do. That's all I need to do in the next hour. The rest of this is code that you can look at on your own. And then I also going to ask you to go back and look at the projects you're working on, whether they're personal or at work, and then also see where this first release of generics could potentially fit in and experiment with that. Now, in the README, I do have links to the draft document over here. I have a link to the Go playground. I'm not going to be using that. I'll run everything on my local machine. But the team did put up a playground. It's up to date all the time with the latest bug fixes and changes. And it's running the transpiler that they've built right now. So this isn't actually coded in the language yet. What we have is a tool that can transpile the new syntax to existing syntax, and then we can build and run it. Now, I've pulled out of the draft document, I'm not going to read this, the high-level overview of what the current draft is looking to support for the first release. This is a living document, so this could absolutely change. We could identify we didn't need something here for the first release. We could identify that we're missing something that's critically important, but we won't know that until we spend more time and get more feedback. So I'm not going to read that, but a lot of this is what I'm going to try to present to you in the next hour. I've also pulled out the omissions. These are things that right now we're not looking at all in putting in the first draft release. That doesn't mean they may not get in, and it doesn't mean that this won't ever get in. To me, generics is a multi-release type of feature functionality, maybe over the next 3 years once we start. So as the need arises, more will be added over time. But right now, this is stuff that I won't be showing you because it's currently not part of the draft. Again, I'm not going to read that. If you're looking to run the Go-to-Go transpiler on your local machine, I also have instructions here on cloning the source code, checking out the dev.go-to-go branch, and then building everything. And that's what I'm doing here. I'm going to be running the latest version of the transpiler basically as of about 4 days ago. There weren't any updates today that I saw. So that's what we're going to be running. And I'll be going again through those first 6. Okay, great. With all that said, I'm going to jump in. I am going to hold some questions off until the end. Feel free to chat, and then I'll do my best to answer everything that I can. But let's start here with trying to get a basic understanding of what the syntax currently is looking like and why we need it at all. All right. So let's start here. Let's say I wanted to write a function today in Go that would accept a slice of integers and be able to print those integers through this kind of linear traversal, right? So I'm going to do a linear traversal across the slice, and for each value in the collection, I'll display that value with a space, right? So you can see here that it's taking me about 5 lines of code with a header and an carriage return there to write this code to take a slice of integers. And then if I wanted to do the same thing, but for a slice of strings, I would at this point have to write another function. Maybe I'm calling it print string on line 21. And this one would take a slice of string. But if you look at the 5 lines of code that I'm writing here to do both operations, I mean, they're really identical. Technically, the only thing that's different is that this is taking a slice of int. This is taking a slice of strings. And I would argue that Go developers at almost every level could read and maintain this code here, right? Even if you've just been coding in the language for a couple of weeks, I would argue that this is code that you can consume and understand and read. So you can see here these 5 lines of code. Now, if I wanted to write a function that could now print floating point numbers, well, right, I'm going to have to copy and paste this and change out the string or the int for the float. All right. And we can do all of this today. But it would be kind of interesting if I could write one print function that can work with both, say, slices of integers and slices of strings. Now, I can absolutely do that today. Here's a version of a print function that's leveraging the empty interface to accept a slice of any type. Technically, the empty interface will let us pass data of all types, right? There's no constraint on the data that I can pass in. But moving from the 2 concrete functions that I wrote, I could use the empty interface to accept that slice of int or string, and then perform a type assertion right here on line 37 to determine was there an integer or slice of string passed, and then perform that linear traversal. Now, I wouldn't go so far as saying that this is a generic function. All we've really done is taken the 2 functions that I wrote and moved them into case statements, right? Applying the type assertion. If I wanted to work with a slice of floats, I have code to write. I got to write now another case for that slice. So all I've kind of done at this point is consolidated 2 functions into one, leveraging the empty interface and type assertions. But then the question is it possible today in version 1.14 of Go to write a generic function of print? And the answer is yes, there absolutely is. Here is a generic version of my print function. It's using the empty interface again to accept that data of any type, those slices of int and strings. But it's using the reflect package to do the bulk of the work. You can see here now on line 58, I'm calling reflect.value of, which allows me on 59 to do a kind comparison to validate that it's a slice. And if it's not, I'm going to return on 60, but this isn't really good. I got to do maybe some better error handling, even though that kind of changes the API a little bit. So there's a little bit of work there. But I can do my linear traversal. I mean, on line 62, I can't use my for range, but I can iterate over that I. And with a little studying of the reflect package, I can index into the slice and use the interface call to get the value back out, and I can print it. So this is truly a generic function. I can use this for the slice of int, the slice of string, and the slice of float. The thing is we went from like 5 lines of code to almost 10 lines of code, right? I've increased the complexity in terms of readability and managing this piece of code. Even I'm not that familiar with the reflect package. I love the reflect package. I think it's an incredible tool when used for the right purposes. But trust me, I had to look up the documentation to write this code. It wasn't as intuitive as we saw the other 5 lines of code. But it is a generic function nonetheless, and when we run this code, you'll see that. So the real question now comes here is there value to be able to write a generic version of this print where I could leverage the same 5 lines of code I wrote here, that again, I said I would make an argument that Go developers of almost all levels could comprehend, read, and maintain, as opposed to having to write code that is really much more complex. The question is there value in that? I think there is. And this is one of the problems that generics can solve in the current draft form. So on line 75, I've showing you for the first time a generic function. Now, before we break this down, just look at the 5 lines of code that I've written inside of it. It really is almost, if not identical, to the 5 lines of code I wrote for the slice of int and string. I mean, other than some labels, we're using our for range, we're using our print. So to me, there's some value in that, right? But let's break this down because I want to share with you the syntax and what I would call the problem space as relates to these new syntax we need for generics. I'm going to do that by just pulling this out for 1 second. Now, if you look at the function the way it is right now, what this function is saying to us, it's saying to the compiler that I will accept a slice of type T, where in this particular case, the compiler is assuming that we are going to define type T in the program before we attempt to build or compile this program. In other words, the compiler is assuming at some level we do something like this somewhere, right, before compilation. So what's important here is that we need a syntax that somehow tells the compiler, look, hey, I'm not going to define T. I'm not doing this work. Either you're going to have to define or figure out what T is, or I've got to tell you what T is based on all existing types that exist at the time I hit that compile or build button, right? In other words, I can't just write generic functions and just say T because the compiler's not going to know. So we need a way of telling the compiler that T is a generic type, a type to be determined at compile time, and I'm not going to be the one defining it. Now, in the current draft, we're using this syntax to do just that. We're currently using the square brackets, though the very first implementation of the draft did use parentheses here, and it's still an option that we can look at and play with. I have found pretty quickly that the square brackets do help with some readability, and I'm going to be using them in the presentation. Now, what this is, at least to me, is a list of types, a list of generic types to be determined at compile time. This is how we're going to tell the compiler that don't expect me to define T, the T's got to be defined there at compile time some way, somehow. Brilliant. Now the compiler is not going to be looking for T necessarily somewhere where I'm going to define it. And now T can be any sort of type we need to satisfy the code that we've written. Nice. So we now have a function here that can work with a slice of some type T that we can then write code like we were doing when t was an int, when t was a string. We can write a concrete implementation of the function, even though we don't know what t is until compile time. And we're reducing the complexity here that we had related to the reflect package in this particular case. We're reducing the complexity around the use of the empty interface, where we don't really know what the data is until we begin to inspect it. We're now writing a function where we don't necessarily know what t is, but we know it's a concrete type that we can apply this type of operation to. Pretty cool. Now, let me run these functions so we can get a general sense of it working. So you can see on line 86, I've constructed a slice of int, on 92, a slice of strings, and I'm using all 4 functions, passing that slice in the same way. Now, I'll move over to the terminal window here, and we go into O1. I'm hoping this is large enough. If it's not, somebody just unmute and chime in. We can build and run this code. Notice the extension is .go2 if you haven't yet. Again, we're going to have to use the go-to-go transpiler. And in that branch that I have, the go-to-go transpiler shows up as a tool. So go tool, go-to-go. And then we're going to use the run command across that. And I'm going to provide it the source code file. And we can build and run that program. And you can see the output is exactly the same for all 4 functions for ints and strings. Now, the cool part here is if I now decide that we're going to use some floating point numbers, right? Let's just have some fun here for a second. And this is going to be a float 64. Well, we know that I'd have to write an entire new function if I wanted to do something like print floats. We know I'd have to add a case statement for print assert. But as I kind of already suggested, the reflect package is technically giving us the ability to write a generic function as much as the print generic did, just reducing the complexity, right? And then the generics letting us write the concrete code. So if everything is right here, there it is. I'm able to now output that slice of floating points without having to write any more code, just make those calls. In this particular case, we're using the reflect package. In this case, the compiler is turning around and going, okay, I know, I now need to implement a version of print that accepts a slice of float. Now, we're also seeing something here that might be obvious to us, but it's work that has to be done. You see, the compiler right now is able to infer what t is based on the data that we're passing in. There are times, however, where we might, or the compiler may not be able to infer type information, in this case at the call site. And so that same square bracket syntax that we used to define that t is going to be a generic type to be determined at compile time can be used as a way of saying, don't worry about inferring the type, compiler. I'm going to tell you what t is. T is now an int. T is going to be a float 64. T is going to be a string. So we can also provide the compiler, in this case, at the call site, what t is. But that would be really tedious if that's something we had to do all the time. And so the idea here is that the compiler wants to be able to infer the type based on the data being passed in. And it can do that in this case, because though we've defined t as a generic type, we're using it in the first parameter. And the compiler can see, oh, okay, t must be an int, t must be a float, t must be a string. We're all good. Really, really nice. So one of the things that I'm trying to do as I experiment and convert code using the new generic syntax, well, one thing I'm trying to do is where does it make sense and where doesn't it? And I'll show you some of that before we're done. I'm starting to try to see, are there smells? And one smell I'm starting to develop is when I have to explicitly pass type information at a function call site. That's tending to become a smell for me. Remember, when I say smell, I don't mean that it's absolutely wrong. I just mean that maybe there's a better way to do it. And every time I've written a generic function so far where I was like, here it is, I finally found a reason where I have to pass in type information. I've sent it to the language team and they've said, well, Bill, you know, if you write it like this, we can now infer the type. And I'm like, oh, yeah, okay, great. So I think that's one of the things I'm looking for as well. And I'm looking for on these function call sites, is it possible for the compiler to infer the type? And if not, am I doing something wrong? Am I forcing generics here when I shouldn't? Or am I just making things more complex? And these are things I want you to think about as well if you take some time to start playing with the new syntax. Okay, so I've given you the base generic syntax here using the square brackets to denote, in this particular case, type identifiers that need to be determined at compile time, not determined by us. In other words, we're not going to be declaring ahead of time. We're going to use these square brackets to do that. And I showed you how we could also be explicit on the call side here to say, don't worry about trying to infer it. I'm going to tell you what it is. It's going to be an int. And obviously all that has to match up. Okay, great. So this is the first example with the generic functions. Now, this is all great, but I would argue that for us to write any meaningful software in any programming language, at least the apps that we've been building here in Go, we need to be able to define data, right? We're all working with different types of data. And so this can't just be applied to functions. This also has to be applied to I'd like to be able to define some types that are more generic. Let's take a look at how the syntax works as it relates to being able to write some generic types in Go. Okay, let's go through a little bit of the same progression that I just went through. Let's say I wanted to define a vector type, in this case worked with integer values. Well, I can define a type named vector int whose underlying type is a slice of int. I'm doing the same thing on line 18. If suddenly I wanted the same concept but for strings, I can define a type named vector string whose underlying type is a slice of string. And if you look on line 13 and 20, I've added behavior for vector int and vector string. I've added a push method, which is leveraging the append function to add, in this case, an integer on line 13 or a string on line 20 to this vector. Now,
I might just mention that there's a kind of bug there, which is that v vector string they should both be pointer methods, I think, because otherwise they won't do anything.
Well, if you notice,
you're returning the value. Sorry,
yeah, I'm using the value semantic mutation like append.
Sorry.
Yeah.
Sorry about that. Yeah,
it's all good. So you could see here once again that the only difference in the implementation of push is really the type information for on the receiver side, really, right, and on the parameter. Now, I am getting a little lucky, let's be honest here. Append is technically a generic function. I mean, I could make an argument that Go has generics today because the built-in functions are technically generic functions. The problem, however, in me saying that, is that the mechanics that the language gets to use to write these generic functions like make, append, copy, are not, they're not presented to us, right? We can't use the same language mechanics that the language has to write these kind of generic functions, but I could make the argument again because of reflection and because of the way these built-in functions work, Go has generics, right? They're just not extended to us. But it's that idea that's really allowing this code to be the same, because append can work with a slice of any type and a value of that same type and perform that append operation. But again, if I wanted to work with a slice of float, again, I have to write another type and basically copy these lines of code and just change the type information. So then the question is, well, could I write a single vector type that could do it all? And the answer is yes. Again, here comes the empty interface again. I can write this vector interface type. And again, if you look on the implementation of push for string or interface, it's using append, our generic append function, to do all that. There really isn't any difference. But I will argue that though the implementation of the code isn't adding any more complexity. The use of this vector does. Because now we've really changed the semantic here for this vector. This vector isn't tied to just one type of data. We can push any type of data into it. We can mix data types in this vector. And that can cause problems on the usability, because now we can't just assume that there's integers or strings or floats in there. So even though I can do this, the semantics for me are really different between what a vector string is, just working with string, what a vector interface is, which is really not tied to any sort of data constraint. And I think here's where generics, again, come in and solve a nice problem, because what generics are now going to do is let me define a vector type of some type T to be determined at compile time, and restrict the vector to only values of that type T. I get back to the original semantics of a vector of a single type, as opposed to the empty interface kind of changing the semantics on me and making things a little bit harder around usability. Now, let's go back and just study the syntax again. I'm going to pull out the new syntax with the square brackets. Again, what I want to do is tell the compiler in line 46, I'd like to define a vector whose underlying type is a slice of some type T. Again, I just can't use T like this. The compiler would assume I'm defining T. So we bring in the square brackets, and now we're telling the compiler, don't expect me to define T. We're going to define T at some point before you or at compile time. Let's just say at compile time, you will know what T is going to be, but it won't be necessarily defined by me. And you can see again, the implementation as compared to the concrete implementation is the same. This maybe gets a little tricky on the receiver side, because you can't just say vector generic. We still need to specify that it's a vector generic of some type T, where we're passing a value of that same type T and returning the vector generic of type T. But again, append is already a generic function, and so it all kind of just works that way as well. But let's take a look at the usability of the different functions. Let's kind of start here. So you can see I'm constructing a vector int set to its 0 value. I've put all the push statements on one line just to keep the code a little, vertical there. But I can only push integers into this vector, which to me is a good thing. And then to show you that I want to work with the concrete data directly, I am specifying in the print statement the %d. Now, we could argue that print is a generic function as well, leveraging the reflect package, right? That's what it does. It can output these values. But in this case, I just want you to look at that I'm using %d here, which is really going to restrict us to use an integer on that call. And I don't have to worry about it. I know this is only integers. Same thing as we look at the vector string. I'm going to construct set to its 0 value. We can push those strings in. I can use %s here because I have a guarantee that as I range over this vector, it's only strings. And this is when that usability for me breaks down with the empty interface here. Because if you look on line 71, I'm interlacing integers and strings, right? The semantics have changed. And if I now want to leverage the same print statement with the %d or the %s, I'm back to doing the type assertions. And what's worse, if I throw a floating point number in there, it requires more code, right? So to me, this is one of those interesting things where the implementation complexity didn't really increase, but the usability ends up increasing and or the semantics changed. So what does it look like using our generic vector? Well, look on line 82, and you're going to notice the use of the square brackets during the construction call. And remember, I talked about when we were calling functions, how we can explicitly provide the type information on those generic functions, though we would prefer the compiler to be able to infer the type. When it comes to these name types, these generic types that we're declaring, there's no place where the compiler, at least today, can infer that type information. So we're going to have to explicitly provide that information at construction. So what you're seeing me here is say to the compiler, let's construct a vector generic where int will be the underlying type for that slice, or where string will be the underlying type for the slice. And now the compiler can go ahead and implement push with integers and push with strings. And we're now walking away again from all the complexity of the type assertion, and I can work with the %d. And we could go ahead and build this code. We can run it. We can see the interlacing here, which was with the empty interface. We can see that. And what's nice is, once again, I can just come in here from a usability perspective, right? I don't have to really write any more code here. We could just say, okay, this will be a float, and we'll work with floats here, and we'll just very quickly do this. And the compiler here, you know, even there I say F, and I can say this is F. And basically now it's just more of an implementation situation here, right? I'm not implementing another generic type. I'm now just telling the compiler, can you create one for me that works with floats? And now we see that. Actually, I didn't change the labels, but you get where I'm going there. So when it comes to these named types, right, or these generic types, okay, where the underlying type or some piece of the type, even if it was a struct, where some aspect of a field or the underlying type is going to be based on a type to be determined at compile time, we're going to still define that identifier list of types. And in this particular case on construction, we're going to have to tell the compiler there's no way to infer it, what in this case T is going to be. But we have the ability now to create these generic types. Okay, brilliant. So I've shown you the generic functions. I've shown you some generic types. Let's continue to kind of explore both of these ideas. And let's get back to generic functions for a second. The function that I showed you, which was an output function, was leveraging the idea that print can already leverage the reflection package to identify how to output something, right? There was no real constraint that we had to put on the data that we were passing in for the code we had to write. But in reality, we're going to write lots of functions that are going to create constraints on the data. In many cases, behavior. In many cases, we're going to use methods against the data, and we've got to have a guarantee compile time that that data exhibits the behavior. So there has to be an aspect of the spec where we're able to define constraints on what data we are allowed to pass in for that type T to be defined at compile time. So let's look at constraints. Now, at the beginning of this example, I'm defining two user-defined types, user and customer. You see that on line 13 and 22. And both of them have implemented a method named string that returns a string. And these methods here, what they're doing is pretty printing, basically a form of user and customer in a JSON-like syntax, right? Now, for those of you who are more experienced with Go, you might also recognize that this method string that returns a string also implements a special interface in the funct and log patcher called stringer, right? They implement the stringer interface. Okay, so I've got this ability to pretty print users and customers any way I want. And I could go ahead now and do the following. On line 38, I write a function called stringify, but it's specific to just users. So I can accept that slice of user. And what it does is returns a slice of string for the pretty printing of every user that we pass in. So we construct a new slice based on the length. We do our linear traversal again using our for range. And we leverage our generic append function. But to access the pretty printing functionality, we've got to call this method named string explicitly to be able to do that. And we do this. And then if I want to do the same thing with customers, well, it's a copy and paste again. And really the only code that's changing is the type information related to not using users anymore, but customers, and in both cases, we're leveraging the string method to give us the output that we want. Once again, could we write a generic function in Go to do this? And once again, yes, I can use the empty interface, I can use a type assertion, I can use case statements, but as we already talked about, this isn't really generic because if I have another entity, I got to add another case. All right, could I use reflection? I can. But look how much more code is involved. This is a generic version of stringify, empty interface, accept a slice of any type. We've got to validate that we did get a slice. I'm returning nil for that. I don't know how valid that is in terms of a change in semantics. We don't really assume that if there is values in the slice, but minus all of that we can have discussions on, there I am constructing the slice. I'm using a linear traversal. I can't use my for range, but I can iterate over I. And then with a little bit of work, looking at the reflect package, I can index into each element, and I can even validate if that value at any given index has a method named string. I do a little bit more work, I call it, and then I do the append, and I need another string call to get that in there. Whew. I wrote a generic function using the reflect package. But let's go back, right? We went from 5 lines of code to, what is that, 15 or 10, 15, 12 lines of code here with a lot more complexity. Again, I would argue that the average Go developer at almost all levels could have understood the concrete implementations. This requires a lot more work, and this took me a little bit of time as well because I had to study the reflect package API. And this looks a lot more scary. It doesn't, but it works, So again, I'm going to come back to, is there value in writing the stringify function in a more generic way that lets us use our concrete implementations? And again, I think there is. And here is that generic version of stringify. Again, let's just pull this out and we'll break it down a little bit at a time. Again, I want to write a function that can take a slice of t to be determined at compile time and return the slice of string. And I want to write code as if t was a concrete type that we defined, right? That I defined. This is code that we all have a lot easier time consuming, reading, and maintaining. But once again, we have the problem where I'm not going to define t. It has to be defined at compile time. So we add the type list using the square brackets. But now we have one more problem. You see, this code assumes that the value associated with the slice, a value of type t, has a method named string. And the compiler has to give us that guarantee. The compiler has to make sure that when it generates or constructs a version of this function, that whatever t is does have a method named string. So how do we apply this constraint? Well, I would argue, how do we apply constraints today? I mean, I can write a polymorphic function today. I could call it Bill, and I could say Bill, right? I could say that what Bill does is it accepts a value, a concrete value, but not based on what it is, based on what it can do. What this function, I call this a polymorphic function, says is I will accept any value or any pointer that knows how to string, right? We're using interfaces already today to define constraints on behavior that data must exhibit in order for it to be used, let's say, in this function call. So I think there's a nice match in being able to say, can we leverage interfaces to apply the same type of behavioral constraint to our generic functions when the constraint has to be present? In other words, in this particular case here, since we have to guarantee that value has a string method, the values of type t have a string method, by applying the interface information here, now we're going to say t is a type to be determined at compile time that implements the string or interface. It gives the compiler what it needs in order to give us the guarantee that that behavior is going to be there. So this idea of continuing to leverage interfaces to apply constraints to what data we can actually pass or infer around what type t is going to be. Okay, let's take a look at how this works. So I've got my slice of users, and once again, I can pass them into all 4 functions. I've got my slice of customers. I can pass them into all 4 functions. We can move over to that example, and run it. You see the pretty printing. I'm not going to waste time creating another entity. You get that. We see that already. What I do want to do is get rid of the constraint, though. Let's just say I implemented the function like this, where I'm not putting a constraint on any data of type T having a method named string. What does the compiler do? I like the error messages that are already coming out of the compiler. You can see here it's saying on line 114, value string is undefined, type not bound for type T. I mean, it would be really the same kind of message we would get if we wrote a polymorphic function and the data didn't exhibit the data. It's kind of the reverse of it maybe, but it's the same kind of idea, right? And so now by putting the constraint back in, the compiler says, okay, everything's good. So we're seeing here how we can leverage the interface to apply a constraint on what T can be based on behavior that we know T must exhibit. Okay, pretty cool. All right, and I personally think that that kind of continues to fit in with Go and where Go is today and its syntax. One of the things I want you to be thinking about, maybe chatting and talking about is, does it still look like Go? Does it still feel like Go? Or, right, and I think at this point, we're on mark with that. But there's more. Behavioral constraint is one thing, but there's another type of constraint that we have to consider. Now, some could argue that it's behavioral as well, but I like to think of this as a constraint on the property of the data. What if I wanted to write a function that could add 2 values together? Well, now we have a problem, because though I can add integers and strings and floats, I can't add users and customers, right? And Go doesn't have operator overloading. I can't write a method named operator plus to give users and customers the behavior. And so we have this situation where sometimes the constraint isn't directly on behavior, but on properties of the data. And how do we allow, or how do we as developers apply those constraints when this is something that's really new for the language? Well, let me show you what the current draft is suggesting when we need to apply what I'm going to call a constraint on the property of the data. Now, I really want you to focus on line 16 for a second. And notice that I'm writing a generic function named add that takes 2 values of type T and adds them up to return a new value of type T. And again, the problem here is that not all values support the plus operator. I cannot use a user and a customer like you saw defined before, but I do have to apply a constraint to just that data that can be used in this plus operation. So the current draft is suggesting this syntax for applying what I'm calling these kind of property level constraints. And it's a type list. It's a list of types that now are the only data types that can be used in this function. Now, one thing I want you to be aware of is that Go can leverage the underlying type of things and still match against this list. So if I did a type named Bill, which was a slice of string, in this case, let's say this, string. Well, Go, I could still use Bill in this because string is the underlying type in a sense, right? So one of the nice things here is that when we're defining these type lists, we don't have to necessarily worry about being explicit down to say Bill. That string, in many cases, the underlying type, can be inferred and then leveraged. But you can see here, and we're going to run this code, that the idea right now is to define a list of types that we know can work with this operation, and that gives us the constraint we need. Now, I will tell you this. This is probably, at least for me, the first deviation away from syntax looking and feeling like Go. And this is an area of the design draft that the language team has expressed to me also some concern about. And their concern is this, that at least currently, with the way the draft is written and the way everything is implemented, when you have an interface that has this sort of type list, it can't be used anymore to write these polymorphic functions. It's kind of now restricting the interface to just being used in a generic function declaration and no longer being used everywhere. And the language team isn't terribly happy with that. Now, I don't know what direction this ends up going in, and this is an area of the draft that they do want some thoughts and input around. You know, maybe at the end of the day, we allow the type list to also restrict the type of data that can be passed into build. Maybe there's a way of not putting this inside the interface and still having a way to apply this type of constraint for the add function. I don't have any answers. I've probably have spent 15 or 20 minutes thinking about this, and I'm drawing a blank. Right? This is not an easy problem to solve, but this is what we have right now. And though I think they would like a different solution that could look and feel more like Go and not break these polymorphic functions, it's quite possible that this ends up landing when this gets released a year or so from now. So if you're looking at this going, Bill, you know, you're not the only one, right? And again, members of the language team working on this are also somewhat iffy on the syntax. But I want you to appreciate that it's needed. We need a way to define this type of constraint. And right now, the draft idea is to put it inside the interface. Now, let me explore this a little bit more with you. Look at this function that I just wrote called index. Index, like sometimes it just helps me to take this out so I can just read it sometimes. So index is going to take a slice of some type T and a variable of, or a value of some type T. And the idea is to range over that slice. And then for every value that we pull out of the slice, compare it to find. And again, we have this situation where not all values that we define can be used in this if statement, right? Like we can't use two slices and do this comparison. So we have to define a constraint again. And so here's type T. And the draft is also experimenting with this idea of some pre-declared type constraints. And here's one of them right now that exists, or it's implemented with the draft. It's called comparable. And so there may be opportunities where we don't necessarily have to worry about any of us or defining these types of constraints. Maybe they can be pre-declared in such a way that we can just leverage them like you're seeing here for comparable. So this is an interesting aspect of the draft too, and with the pre-declared type constraints. Okay, and one thing that just came to mind that I want to share with you here is that there is no constraint on what you want to name these generic types. When it comes to collections, right, like these slices, I'm finding that using these single letter variable names seems to work. And maybe it's something that I got from C++ and Java, so I'm carrying it over. But I do have other examples in the training, especially when there's something very specific to input or a return value where I'm using longer names, okay? So you're not restricted to what this identifier can be named. It's really gonna be around readability. But I have asked the Go team at some level that before this gets released, that they do provide a nice set of guidelines and idioms and lots of code examples that we as a community can leverage for things like, you know, naming these generic types, whether it's a collection type or maybe represents a struct or something like that. And so there's a lot of work to do. We can talk more about that at the end of the talk. Okay. Let's look at one more kind of scenario here. And I'm forcing it. What I'm about to show you, I'm forcing because I cannot find a practical reason to do this. It is part of the draft, and I am struggling here. So if any of you ever find a practical reason to do what I'm about to show you, I would love an example of it. And I think this is another reason why I want people looking at the code they have today, whether they're personal or work projects, and seeing what actually is usable and what isn't, right? Because that's going to help reduce what we need, or reduce complexity, and then make sure we have what we need. But let me just show you this, okay? So person type with a match method that can just match the names, a food type with a match method that just matches the name. All right, we've got that. So I go ahead and I want you to look on line 75 for a second. And I wanted to write a function called match that took a slice of some type t and a value of type t defined, range over the slice, and use the match method, okay, for every value in the collection here, in the list, passing find into it. And if that was true, return the index. If not, return -1. So I wanted to write a generic match function that could do a linear traversal and leverage this match behavior for every value in the slice. So we already know that if I want to make this a generic function, right? If I want to make this a generic function, I have a match constraint. I need some sort of interface that defines match behavior, but it's also match behavior that could take a value of any type t. Okay, so if you go back to line 70, right above, you can see here that I'm defining a generic interface. I'm defining an interface called matcher, which is an interface, but there's going to be a generic type t that's involved. And if you look on line 72, I'm using that to define what the match behavior is. So you need a method named match that takes a value of some type t based on what's being passed into this match function to satisfy the signature here, which is what we're getting. All right, and that's reasonable, right? Like I see a lot of that happening as we move towards these more generic functions, and we have this sort of behavioral constraint. What I'm struggling with finding a good example of is what I did on line 71. Is there ever a reason? Is there ever an actual practical need to have an interface for this generic function that not just defines constraint on behavior, but maybe on properties as well? Now here I'm saying that the only types of data that I will allow to be passed, in this case, into match is person and food values. It's kind of a silly constraint because really all I care about is what? That you exhibit match behavior. But I wanted to show you that you're not restricted in having a mix of behavior and a type list. But as soon as we apply the type list, this is going to take precedent over this match behavior. I mean, this is all I'm going to be able to pass into this function. I'm not going to run this code. You get a sense of that here. But I'm struggling to see, is there really ever a need to do both? And if there isn't, if we really find out that there's not going to be a need to really do this, this might in and of itself help with the other problem of this list even being here. One other thing that sometimes I'm asked is, can you provide a list of different interface constraints? And the answer is no. For any given type, it has to be one interface. So you'd have to define an interface that would have all of that behavior that you want to constrain against, all right? One interface per type. But it's interesting as we explore this, that maybe that in and of itself solves the problem. I don't know. But this is an area of the draft that we have to spend more time on. Okay, I want to share two more examples with you here before I'm done. I'm in pretty decent time, so that's good. This one's quick. All I'm trying to do here, not going to run it, is show you that you can have more than one type or type identifier declared in the list. Okay, you're not just bound to one. All the examples I've shown you right now are just type T, but here's where I'm saying type L, which represents the first parameter, a list of labels, type V, which will represent that slice of values, right? Now, if we look at the implementation again, we see that I'm assuming that V, not assuming, I'm declaring, mandating that V has the string behavior. So you can see here that I need to apply that behavioral constraint again for V. Now, in the current draft, what happens is if that you apply a constraint for one type, you have to apply a constraint for all types. If I leave the code like this won't compile. So you might see in code sometimes the use of the empty interface as a constraint because some other type in the list has a constraint. And that's why you see the empty interface here. So if you see that or you run into this problem, just a heads up. Now, I don't know what the issues are with supporting this. All right, I've never asked the language team. So this might end up being something they can do. It may not, I'm not aware. But I ran into this at one point, so I'm just sharing it with you. You can have multiple types in the list or declare multiple type identifiers in the list. And as soon as one has a constraint, they all need a constraint. The empty interface is how you apply a constraint that doesn't constrain, right? Okay. I'm going to share this last piece of code for number 6. And I'm going to leave 7, 8, 9, 10, and 11 for you to work with or to review and play with and to learn from. Now, before I open up number 6, I'm going to be opening up a little bit of a can of worms here. The code I'm showing you is not necessarily something I think I want people doing in Go. I have a feeling that people are going to do this. I have a feeling people are already doing some of this. So I'm going to be expressing some of my opinions that you may not agree with. That's fair. I'm telling you that up front. But it was an experiment that I ran in looking to see if I could reduce some interface pollution using generics. All right. So let me break down this, and it also brings up the need for or situations on returns of generic types. Okay. Let's start with what I'm doing here. So the idea was, let me define a type named user, like you see on line 15. And then I write an insert function on line 21. Now, the insert function's using that value semantic mutation that you saw before. I'm passing in a user where, let's say the ID is 0 because I don't need it in the call. All the intelligence for doing the insert is inside this insert user function. But after I execute the query, I get the new ID back from the database, and I use that to set my copy of the user value and then return a new user value out with the ID. Personally, I like using these value semantic mutation APIs because I think they keep the data clean. I got my own copy of user in, I mutated that, and I give the caller a new version, and they can choose to have both, or they can choose to replace. But if they replace, they don't get stuck with kind of these two different user states, right? I personally have found that this type of mutation, when it's reasonable and practical to use, adds a lot of value. And the key here is getting that ID, right, back from the database, letting the database generate that, and then assigning it. So here it is, an insert user has all the intelligence, and really the core intelligence is the query itself. Everything else is kind of already a generic function. This is generic function using reflection already. This returns an int64, no big deal. We have to do the assignment, we do the return. Okay, so now in my program I have a customer, and now remember, like, I'm writing CRUD, right? I hate CRUD. CRUD's the worst type of API. They're just so complicated to write. So now I'm going to do an insert for a customer. And once again, the customer has an ID. So I follow the same pattern and I write another insert function and I pass the customer in. Here's the query. We call execute. I get the last ID. I set the ID. I return it back out. I mean, like what, 99% of this code is the same. The only real difference is having the query here, right? And knowing the arguments that I have to pass to execute that query, as opposed to the arguments I need to pass to execute query for that. I mean, there's intelligence here. Everything else is virtually the same. So I look at this and I go, when somebody runs across this, what do I think they're doing? And I start to get a little nervous because, again, these are my thoughts and opinions. One thing that I try to avoid quite a bit are what I'll call entity-based interfaces. Interfaces that are defined for a user or customer, because they're not interfaces that can be reused, right? They're really tailored and specific to some problem. They're not even really well defined around behavior. I have a strong belief that interfaces define behavior, right? And the concrete types define those entities. But I see people wanting to write interfaces like this on line 70, right? Where this suddenly becomes a user. And to me, I think these types of interfaces cause more problems than good. And on line 73, I now see the dreaded setter method for setting the ID, right? And so I've seen code like this. Let's add a method called query that returns a string and arguments and set ID. So what I can do then is write a insert maybe function, right? That takes an entity, okay, whatever that entity is. And now I've got all this code working. I can call query for the string. I can call arguments for that. I can get my last ID and I can use my setter and all that's good, right? And again, I start to shudder because I think these types of interfaces work really well for the network connection. Like netcon is a beautiful, what I call like an entity-based interface for connections. Russ just shared a really cool proposal for a file system interface. I think these kind of device level interfaces can work here. But when it comes to users and customers and things like this, I've just seen more problem than good. So the question came up in my head, would I be able to write a function like this where I could substitute T for customer? The key really is here on line 55. I don't want to write a set method just to make this work. I want to work with the concrete data and access the concrete field ID, creating a guarantee that whatever data I pass to insert will have a field named ID. And what's kind of cool is the current draft does support just this. As long as I define an interface with a set of types that I am guaranteed to have an ID field. Now, what's a bummer right now is I can't run this code because the draft isn't implemented 100%. This piece on line 23, though the draft supports it, hasn't implemented it yet. So I can't run the code. But I just want you to look at this because, again, I'm not sure I want people writing code like this. But if I had to choose this over the interface version, I'd choose this one every time. Look at what I've done here. I'm defining a function named insert that will work with a value of type T bound to the type list right now for just user and customer. It takes the pointer to the database. It takes a value of type T. It takes the query string and the arguments because I don't want to wrap those in methods. What I'm also doing now is also, reducing the amount of code the user has to make by not having them have to write all of these methods every time they want to work with the API. A big part of this also, though, is right here where I'm returning a value of type T. All right. Now, the execute query call works the same way I wrote it in the concrete version because I can pass query and args. I can call last ID, no problem, assigning it to a local variable. And thanks to this type list, the compiler can validate that both user and customer have an ID field. And now I don't have to use a method in order to do this assignment. I can reduce a lot of code, a lot of interface bloat, and still write a generic function. And then right there on line 27, you can kind of see how the generic insert could be used, where I have a query and I pass the arguments in with the query, and then it's a simple, did we get an error or not? So I think there's some interesting things here with this code. But the other thing I need to show you before I'm done is the return. Now, what this function does is returns a value of type T. But I want you to remember something. Let's go to this implementation here. If execute query fails, I'm returning a literal construction, right? I'm doing a literal construction of a customer on the return, a literal zero value construction of customer on the return. Here, a zero value for the error interface. And we're taught to do this for readability. I like this idiom a lot. I use this, I teach this all the time. But when it comes to returning a zero value of type T, it gets a little complicated. So the current draft provides two solutions to this. On line 114, you see the first solution, where we use the new function to construct a value of type T, getting back a pointer, and then dereferencing that pointer. But that gives you your zero value return. And it gives you the construction on the return. The other option is to declare a variable, maybe called zero, of type T using var. So that will do a zero value construction. And then you can use zero on the return. I think your third option could be doing the construction of zero next to the return site and then keeping it all together. I don't know. This is something that I think we as a community need to eventually come down and identify the idiom or the guidelines around it. But this code also was a result of wanting to show you something more practical around how do we handle zero value returns of type T and presenting to you the two options that are here. And I think through everything that I've shown you at this point, the big takeaway for the current implementation of the draft is areas where the empty interface is being used today could be really wonderful places to work with that generic concrete type. And in cases where maybe we're abusing interfaces, which again, my personal opinion is, to me, I don't really want to see people using interfaces like this. We might be able to leverage generics in being able to leverage those fields directly and not having to turn everything into a method to gain that level of abstraction we need to write these polymorphic, or to write this polymorphic code. Okay, so with all that being said, that's all the code I want to share with you. I think it covers the bulk of the draft in terms of the syntax and what we're going to have.